Okay, so welcome everyone to this edition of our IMSc 60 Distinguished Lecture. So today it's a great pleasure for us to have Professor Gerald Dunne with us. So Gerald is a professor at University of Connecticut. So he is a pioneer in the field of understanding this resurgence phenomena where one can see the mathematical structure of a perturbation series and how to find out non-perturbative physics out of it. And of course, this is one of the works that he's been doing recently. And he has also done several other works in the areas of strong interaction dynamics, mathematical physics. Like he has very beautiful works on understanding the Euler-Heisenberg formalism, on the Schwinger mechanism, and using it to understand Schwinger processes in different kinds of electric magnetic field profiles. And also he has fundamental works on Chern-Simons theories and several other areas. So it's indeed a great pleasure to have Gerald with us, and I request him to kindly give us his colloquium. Thank you, Gerald.
All right. Thank you very much. Can you hear me okay?
Yeah.
Yep. Okay.
Yeah, we can hear you.
Okay. Well, first of all, congratulations to the Institute on this big milestone. It's a wonderful institute, and we look forward to many more celebrations in the future. And thank you for the invitation to speak. I'm going to tell you a little bit about this fairly recent work about relating perturbative physics and non-perturbative physics, which goes under the mathematical name of Resurgence. And I'll keep this fairly general because people may not be familiar. I want to give you the basic ideas behind it. So let me begin with some motivation. There are some problems in quantum mechanics and quantum field theory where we need to go beyond perturbation theory, when there are very strong interactions, or when things are very non-equilibrium, or when there are very, very strong fields. This is an image here of some of the electromagnetic fields in plasma surrounding electron bunches at SLAC. And here's an image of sort of an artist's image of some of the processes near a black hole where there are extremely strong fields and things are extremely non-equilibrium, and where perturbation theory is not much use at all. So the way to deal with this is to go to the path integral representation of quantum mechanics and quantum field theory. So this is this great discovery of Feynman that we can regard amplitudes in quantum theory for a transition from some initial state to some final state governed by some Hamiltonian as a sum over all the paths connecting the initial state and the final state. So in quantum mechanics, this is written as a sum over all paths with some phases that involve the classical action for each path. So this is a very beautiful idea, and it's very powerful because it gives us a natural generalization to quantum field theory, where we can sum not over paths, but over all configurations of fields, weighted by a phase of the action corresponding to those fields. So already at this level, even though these expressions are very poorly defined mathematically, we learn a lot. For example, we learn why classical physics is expressed in terms of this mysterious stationary principle of an action, which as students were just told came from the blue, but in fact it's just the natural stationary phase approximation of the path integral. When you have actions that are very large compared to the scale h bar, the dominant contribution is given from a stationary point. It also gives us a natural bridge from classical field theory to quantum field theory, where we don't have the option of something like the Schrödinger equation as we have in quantum mechanics. Also, if we consider the Euclidean version of quantum field theory, where this I is replaced by a -1 under some formal Wick rotation, then we learn that these expressions are very much like statistical mechanics, where this exponential factor becomes something like a Boltzmann weight factor. And that's an extremely important idea underlying the very successful use of lattice gauge theory and Monte Carlo techniques in particle physics and quantum field theory in general. But this already tells us that there are two quite separate ways to interpret the path integral. In one sense, we can interpret it as the generator of perturbation theory, because anything in the action that's higher than quadratic order is regarded as an interaction. And something that's quadratic, we know what this means. This just gives some determinant of the operator in the quadratic part. And anything beyond that is expanded in perturbation theory, and that's what's called Feynman perturbation theory. And that's, of course, crucial for doing calculations in quantum field theory. But if this action is more than quadratic, as it is in any interesting interacting field theory, then there's a completely different way to interpret this expression, which could interpret it as a sum over the saddle points of this action. And that's non-perturbative physics, whereas this is perturbative physics, and yet they come from the same point. So if this path integral expression makes any sense whatsoever, they must be related, and they must eventually be the same thing. And that's the underlying principle behind what I'm going to talk about. And understanding how they're related in detail leads to some new insights into the structure of the path integral. So for example, I'll describe what this idea of resurgence is. It implies that these saddle points should be related in very, very precise ways, not just in words. So to continue this physical motivation, I've listed here some of the things we would like to address. One of the famous ones is the so-called sign problem. If you try to represent quantum field theory using a Euclidean path integral at finite density, then you hit a problem called known generically as the sign problem, is that the action under this rotation in the presence of a chemical potential is still complex. And so the interpretation as a Boltzmann weight is problematic. And this is a very famous, still unsolved problem in quantum field theory. Similar things apply to non-equilibrium processes where we have to stick to actual real time. And in fact, just real-time evolution at strong coupling is also difficult to implement using a path integral. Also, quantum systems in extreme environments, such as very intense gauge fields or very intense gravitational background fields. These are the things where perturbation theory is not much use, and we need to understand how to go beyond just simple perturbation theory. So the standard computational methods we learn and use for path integrals are, of course, perturbation theory. Then, as I mentioned, these non-perturbative numerical methods based on Monte Carlo representations. So lattice gauge theory is the most well-known and successful version of that approach. And then there are non-perturbative semi-classical methods, loosely speaking, called instantons, which are also a well-known and well-developed approach to quantum field theory. We can also deal with asymptotics. If there's some very large or very small parameter in the system, if we're in some extreme situation, then we can think of expanding in that extreme parameter. And the underlying idea of resurgence is that it seeks to unify all of these approaches. And by unifying them, you can learn something about each of them independently. And the technical problem boils down to how do you actually compute a path integral? Well, let me step back for a while and talk about the original sign problem, because this problem occurred back in the 1800s in the field of optics, in this work of Airy and Stokes. So Airy wrote a very famous paper in the 1830s about the physics of rainbows. And he was particularly interested in this phenomenon of multiple rainbows, so-called spurious or supernumerary rainbows. This is when there are multiple reflections inside the raindrops. And already at that time, this is a modern picture, of course, but already at that time, people had made artificial rainbows in the lab and observed more than 30 of these repeated rainbows. And the problem Airy was formulating was how to describe this intensity pattern and color pattern in these multiple rainbows. And in doing so, he developed what we now call the Airy function. But what he developed was an integral representation of the Airy function, and it was exactly of this problem. It was exponential of I times something, and he couldn't calculate it beyond just the very first region, which is the main rainbow peak only. Some years later, Stokes came along and completely solved this problem using complex analysis. And in Calvin's obituary of Stokes, he mentioned this as one of Stokes's great achievements, of many of Stokes' great achievements, but he highlighted this as a work of mathematical super subtlety that he transform this problem into something that was completely straightforward. And of course, nowadays, we all learn this in our mathematical physics classes. Here's the integral representation of the Airy function. It's a function of x. Here's a plot from Mathematica of the Airy function. It's oscillatory when x is negative, and it's exponentially decaying when x is positive. But of course, faced with this integral, if you tried to do Monte Carlo with this integral or to try to evaluate it numerically in any way, you would fail. It's completely impossible, especially when x is large, because this integrand is oscillating like crazy, and you need massive cancellations in order to obtain the finite and small answer. Stokes applied the, at that time, relatively new procedure of Cauchy integration in complex analysis. And he realized that what was going on was that as this parameter x changes, you should deform this contour into steepest descent contours in the complex plane, even though it's a real function and it's an integral along the real axis. The actual physics can be dominated by saddle points that live off the real axis. And as this parameter x varies, the saddle points move, and the steepest descent contours through those saddle points also deform and change. And this is a really brilliant insight, a very practical application of this, again, at that time, modern development in mathematics, and it was extremely important in optics and then eventually in quantum mechanics and electrodynamics. It's actually more interesting than this, that at one level you can think of this Stokes idea that when x is positive, only one of the saddle points contributes, and that's why you have exponential decay. But when x is negative, in fact, two of the saddle points, there are only two, but they both contribute, and that's responsible for the oscillatory type behavior. But it's actually much richer than that, because we should actually consider x in the complex plane. You could think here of this as a one-dimensional or zero-dimensional path integral, and x you could think of as a chemical potential parameter. And so in lattice gauge theory, people often work with a purely imaginary chemical potential in order to make the problem calculable, and then try to go from imaginary chemical potential back to real chemical potential. And that's an analog of this Airy problem. So that's why I refer to this as the original sign problem. And what Stokes noticed, here's a picture in the complex plane of the real part of the Airy function. This is the real x-axis along here, and I hope you can see that it's oscillating here, exponentially decaying here. But once you go into the complex plane, you notice that there's this definite pi/3 structure. And in fact, if you rotate by 2 pi/3 or minus 2 pi/3, what was exponentially decaying is now exponentially growing. And if you're a bit naive and sloppy about this, you would think that the rotation just produces the other exponentially growing Airy function, but that's actually not correct. There's also an exponentially suppressed, exponentially decaying piece hidden under this exponentially growing piece. And this is the challenge. This is what's called the Stokes phenomenon. To be able to keep track of these exponentially small contributions, which in some region of the parameters plane may be subdominant, but in other regions, this will become the dominant contribution. And that's what we want to try and do in the context of path integrals. So let me just use some terminology just to make sure we're all familiar with the terminology. What do I mean when I say non-perturbative? Of course, everyone's familiar with perturbation theory. It's very successful. It's well developed. But in some situations, we have to go beyond perturbation theory. For example, think of the Stark effect. We take an atom, think of hydrogen in its ground state, apply an electric field. That's an external perturbation. If you try to calculate the correction to the ground state energy using perturbation theory, in our quantum mechanics classes, we've all done the first order calculation. Sometimes we've done the second order calculation. But it's a series in powers of the electric field squared because of charge conjugation symmetry. However, this series is actually asymptotic. These coefficients grow like 2n factorial. They grow very fast, and they don't alternate in sign. And the reason for that is that when you apply an electric field, there's also a non-perturbative effect. You can actually have ionization. The electron can be kicked out of the atom. And that, in a calculation of the ground state energy, shows up as an imaginary part because this is a metastable state that's decaying. it's exponentially suppressed because it's a tunneling process. And it's multiplied by a fluctuation. So actually, when you calculate the energy, you have this perturbative contribution, but there's also an imaginary, even though you thought you were calculating a real energy, exponentially suppressed non-perturbative because this factor cannot be expanded in powers of the external perturbation. And so this is a familiar example of a general phenomenon that physics, especially in strong fields, combines perturbative calculations with non-perturbative calculations. And the underlying idea of resurgence is that these two pieces are very strongly correlated with one another. And so this type of expression is a prototype of what I will describe as a trans series. So given that simple motivation from the Airy function and the Stark effect, I would argue that since even in something as simple as the Airy function, we need complex analysis and contour deformation to make sense of these exponential integrals, it's very natural to explore these ideas in the context of now infinite dimensional path integrals. So in other words, here our physical path integral, which is exponential of I times some non-trivial function, the action. So this, we obviously have no hope of calculating this on the real x-axis, but maybe we can deform contours to bring this under control. And in doing so, we can understand in more detail the relation between the Minkowski space path integral and the Euclidean path integral. And if we were able to understand that, I would say that the goal to say that we understand the path integral is that this formulation should be able to describe these Stokes transitions. As you change the phase of parameters in the action, you can have certain saddle points appearing and disappearing from the quantity that you're trying to calculate, such as an amplitude, a transition rate, some matrix element. And of course, if we could do this directly in the path integral, we would have a new way of looking at some of these big problems that I mentioned before, such as the sign problem, non-equilibrium physics, real-time evolution, ultra-fast driving of systems. So this is not something that's going to be solved overnight, but I claim that this is a reasonable approach to explore in this type of physics. And the idea that I want to suggest is that we can think of a computationally viable and actually constructive definition of the path integral using ideas of what are called resurgent transeries. So what is a transeries? So there's this interesting, somewhat cryptic quote from Hardy, who wrote, of course, the famous book on divergent series, amongst other things. He wrote this very, very interesting lecture called Orders of Infinity. You can find it online, where he was studying the general concept of asymptotics. And he made this observation that the only scales of infinity that have any practical importance in analysis are those that are constructed out of the logarithmic and exponential functions. So this didn't really go anywhere for many, many years, but in the 1980s, mathematicians took this up from several different directions. And there's a very deep result, usually attributed to Jean Ecalle, a mathematician from Paris, that basically this is all we need. It really is true that we can build all of asymptotics in analysis out of just three basic elements: a small parameter, a non-perturbative term in that small parameter, the exponential, and also the logarithm of the parameter. And if we allow for iterations of these basic objects, so we allow for things like log of log of log of log, etc., then the deep result in this field in mathematics is that those are sufficient to describe essentially anything in analysis. And so there's this very strong conjecture that transeries built out of these basic building blocks are practically sufficient for any of the problems we're ever going to come across in physics. And as a general observation, you're welcome to search through the physics literature for all sorts of different types of asymptotic computations, and all of them fit within this class. I have not yet found a natural asymptotic expansion that does not fit within this class of functions. So more specifically, the idea is to take what you would begin as a sort of perturbative series in some small parameter. So this might be the output of doing some perturbation theory calculation, and extend it to a triple sum over these three basic objects: the small parameter, what we would call instanton physics, non-perturbative calculations, a la this Stark effect that I mentioned, and logarithmic terms. Logarithmic terms tend to appear due to resonance between different non-perturbative terms, but to allow for these three types of quantities with parameters now, depending on these three different directions, if you like, of expansion. And this is what I would call a semi-classical trend series. It's not the most general trend series because I should allow for log of log of log, but for the purposes of this talk, I'll stick to this so-called semi-classical trend series. Now, the mathematical idea here is that this object here is just generically an asymptotic expansion, say at small h bar. And that just tells you something about the function in one particular direction in the complex plane. It doesn't tell you what happens to this function when you rotate or analytically continue to large h bar. Whereas this trend series does encode that. So for example, as you change h bar, suddenly some exponential term may appear or disappear, which you don't see here, but it's encoded in this trend series. And sometimes you will notice that there's logarithmic dependence developed in certain regions. And that's all supposed to be encoded in this trend series. If that's true, and I'll give you some examples to show how that works, but an immediate consequence of that is that if this construction involving these three different quantities makes this function well-defined, the only way that can happen is for there to be relations between the different directions, the perturbative, the non-perturbative, and the logarithmic direction, because their whole purpose is to correct discrepancies if you just stick to one direction. So it's absolutely essential that there be relations between the perturbative regime and the non-perturbative regime and the logarithmic terms. And the idea here is to see if we can learn some interesting physics by exploring those connections. Now, what about the idea of resurgence? Resurgence is a word coined by Ecalle, actually an English translation from the original French. And the idea is that resurgent functions have behavior that repeats at their different singular points. So they display at each of their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or surge up, resurge in a slightly different guise at their singularities. So just look at this picture. Imagine these raindrops at different critical points, different saddle points, different special points of expansion in your problem. And imagine that you know how to study the fluctuations around each of these points. So that's represented by these ripples. And the idea of resurgence is that these are related to one another in very deep and very precise ways. The different fluctuations around these different saddle points are not independent. And there are very strong, what are called bridge equations relating them. The most extreme version of this says that if you know the fluctuations around one particular point, say perturbation theory, the expansion around the trivial saddle point, this information here encodes all of the information about all of the other saddle points. That's the most extreme, strongest version of resurgence. So if that were true in these physics problems, that's absolutely amazing. And it gives us a new way to approach calculations in quantum field theory and in quantum mechanics for that matter. So the idea here is to explore in the context of now this infinite dimensional path integral, whether this structure actually applies, whether we can use it for something interesting, whether we can learn something from it. But the underlying mathematical conjecture is that this is a very general property of essentially all problems in analysis. It's a big claim. So let me show you some things about just ordinary exponential integrals, just to keep this simple. Let's go back to an ordinary integral along a contour. So this is along a contour that goes through this saddle point, labeled by n. So this function has, say, multiple saddle points. Let's label one of them by n. This is the steepest descent contour that passes through that saddle point. So that's a unique curve. its definition is that it keeps the imaginary part of the exponent fixed. So this is a completely well-defined integral. Along a steep descent contour, this thing is completely well-defined. We can calculate it in many different ways. Now, as physicists, what we usually do is we evaluate the leading contribution, which is just the function evaluated at the saddle point. And then we look at the local quadratic fluctuations around it, which gives us some prefactor. And that's what we usually call the semi-classical or the stationary phase approximation. But of course, why stop there? We can go beyond the quadratic fluctuations. We can treat all of the fluctuations as a completely well-defined integral on the steepest descent contour. So if we consider everything else, that will generate a series in h bar, which I write like this. So there are a lot of indices here. So just to be clear, this is the fluctuation around the nth saddle point along the steepest descent contour going through that saddle point. And the subscript r here relates to the order of that expansion. Okay. Now, if this function has another saddle point, at least so that it's more than quadratic, then let's think of the steepest descent contour going through that saddle point labeled M. There's an amazing fact about, which is just absolutely basic complex analysis. If you deform contours and juggle things on here, you learn that if you look at the large orders, so when R becomes large, the index of that expansion becomes large, you learn several things. First of all, you learn that this expansion is asymptotic. So the coefficients grow factorially. It's a consequence of the appearance of the existence of another saddle point. And the corrections to this are governed by a sum over all the neighboring connected saddle points. And there's a plus or minus sign depending on the direction of these contours. But there's a power law, which is the difference between the function evaluated here and here. So it's the difference between the actions at these two saddle points, if you like. So that's a power that goes with the factorial. But the more interesting thing is that there's an overall coefficient, just a numerical coefficient, multiplying this factorial growth. And amazingly, that overall coefficient is the 0th order term in the fluctuations around this point. So this is absolutely incredible. Studying the large order of the fluctuations along this steepest descent contour, making no mention whatsoever of this, studying the large order behavior along here, which is a completely well-defined integral, it tells you of the existence of this other saddle point, and it tells you the lowest order term at that saddle point. And it also tells you the value of the function at that other saddle point. And then if you look at the subleading corrections, not the leading factorial, but the subleading r-2 factorial, its overall coefficient is the next fluctuation term here, and so on. And this is absolutely general. If you want, just pick any of the standard special functions, you can check that this structure exists. It's just a property of complex analysis. And it's a real shame that this is not described in mathematical physics books. It's very simple and it's very beautiful. Let me show you in practice. Let's go back to the Airy function. Remember, the Airy function was the exponential of a cubic function. It's cubic, so the derivative is quadratic, so there are two saddle points. Let me call them plus and minus. The Airy function is very simple, so these fluctuation expansions, we can just do the calculation. There's some gamma functions. And here are the first few terms. Same numbers at the two places, but plus or minus differences. And now, since these are gamma functions, we can ask what happens when r becomes large. Well, you see there are two factorials in the numerator, one factorial in the denominator. So overall, there's factorial growth. And there's a power of 4/3 to the r. So let's rewrite this in the form of that previous expression. There is indeed an r-1 factorial. There's a 2 pi. There's a 4/3 to the r. Now, what's 4/3? 4/3 is supposed to be the difference between the actions at the 2 points. Well, remember, in the Airy function, it's exponential of minus 2/3 times something. So 4/3 is the difference between 2/3 and minus 2/3. So that's where that came from. And then the subleading correction has a coefficient which is indeed the coefficient from the other guy with the minus sign. And this is completely generic, this behavior. There's an absolutely concrete relation between the expansion coefficients near one saddle point and the expansion coefficients near another saddle point. And again, I urge you, if you're curious about this, just pick some other function, some other Bessel function, some hypergeometric function, whatever. Just pick one at random, look at the large order behavior of these coefficients. It's really remarkable. What's even more remarkable is that this type of behavior has been now looked for and found in surprising areas, in matrix models, in quantum mechanics, some quantum field theory, some string theory calculations. And if you think about it for a while, you ask, where is this coming from? How is this possible? And the only natural explanation anyone can come up with is that ultimately this is coming from this argument from deformation of contours of these exponential integrals, namely the underlying path integral representation of these problems. Now that was an example where you just had a one-dimensional integral, just so we could draw the complex plane as a two-dimensional plane. Of course, mathematicians have been thinking about this for a long time, and even going from one complex dimension to two complex dimensions or n complex dimensions is an interesting problem. And this is known as Picard-Lefschetz theory. And it's a little interesting, right? Because you're starting now with an n-dimensional integral, and we want to turn it somehow into a Borel integral, which is a one-dimensional integral. So how did that, when n is 1, that's no problem. It's just a change of variables or deformation of a contour. But in n dimensions, there's a little bit of a problem here. And the solution was found by Picard and Lefschetz that in fact, there's a preferred direction. So near a critical point, which is a point in n dimensions, there's actually a normal form behavior near critical points. This is related very closely to the classification of singularities and catastrophe theory. There's a normal form that has a preferred direction. So what's happening is there's one preferred direction, and then there's a transverse direction, which is locally a sphere. Or here I've drawn it in two complex dimensions as circles. And that's the origin of this name thimble, that this thing looks like a thimble. And this is still a very active field of research in mathematics, even in the finite dimensional domain. And here I've listed some moderately recent works in the mathematics field, just in these complex dimensions. Now it's a much braver step to try to consider this in infinite dimensions, but let's see where we get. All right, so just to recap. Perturbation theory, of course, is very good, but it doesn't contain everything as far as we know. However, this perspective of resurgence says that actually perturbation theory might be encoding some non-perturbative information, but we have to know how to look for it. And so there's this dichotomy of thinking of the path integral as a generator of perturbation theory, so generator of, say, Feynman diagram expansion, which, as we know, is very successful at computing certain things. But we could also view the path integral as a generator not of a perturbative expansion, but as of a sum over saddles or thimbles. And the conjecture, it's not really a conjecture, it's just a statement. If we actually claim that we understand the path integral, we should be able to understand why these two things are related and why they're actually the same thing, because they come from the same point. So there's a very famous paper by Dyson, which has a very interesting history, actually, where he argued that the perturbation theory in QED should actually be divergent. This is not a proof. This is an extremely beautiful paper. It's less than 2 pages long. There's only one equation in the paper. And it's a very beautiful argument. It's extremely tentative, as you can see from his wording here. And he argues in the following way. Suppose you were trying to calculate something in QED. Think of the anomalous magnetic moment of the electron, G minus 2. What do you get? You get an expansion in the fine structure constant. So the fine structure constant is basically E squared, electric charge squared in natural units. So your function will be some series in E squared. Now suppose this was convergent. That means in the complex E² plane, there's some circle around the origin, no matter how small, there's some non-zero circle, such that inside this circle, you can freely analytically continue with no problem and nothing interesting happens. And then Dyson said, well, physically, that can't possibly be true for the following reason. If you try to think of the quantum vacuum ground state of QED, you've got fluctuating electrons and positrons. There's a very big difference between the universe where E² is positive and where E² is negative. When E² is negative, you've got like charges attracting one another instead of repelling. And so Dyson argued there should not be any smooth, simple connection between E² positive and E² negative. And the only way out from that, well, not the only way, but the most natural way, to imagine that there's a cut along the negative E² axis due to this instability, that if you constructed a QED vacuum in the normal world and then tried to change it to E² negative, that would be unstable. Now, this is often misrepresented as a proof. Let me set the record straight. To this day, and this is now, 70 years later, there is no proof whatsoever that QED perturbation theory is divergent. It's a big, outstanding problem. However, everybody that I've ever spoken to thinks that this is correct. This is a correct argument. But just to emphasize how difficult this problem is, Dyson was extremely cautious about this statement. He's very clear in saying that this lacks in rigor, in physical precision. It's only intended to be suggestive. And actually, the 2 years before, he had published 2 very long papers in PhysRev, claiming in the end that after renormalization, perturbative expansion should converge. So he was taking the opportunity to withdraw that claim. And in doing so, he argued that this is a very subtle, very difficult question. But this paper is very beautiful, well worth reading, and it captures an important part of the physics here. Now, if perturbation theory generically produces a divergent series, we need to work out how to deal with that. And there is a well-developed formalism known as Borel summation, which is actually quite physical and simple to understand. It's just an inverse Laplace transform, technically. So you've got an expansion in this small coupling parameter. You make a transform which essentially divides out the factorial growth. Let's suppose these coefficients are growing like n factorial, divides out the factorial growth, and now this becomes a convergent expansion in this transform parameter t. Going back is a Laplace transform, so you do this integral, and if you just treat it term by term, you see that powers of t here just give you powers of g together with an n factorial, which cancels that n factorial, so you go back to where you started. So if you don't do anything more, you haven't gained anything. You've just written a complicated expression as another complicated expression and gone back again. So that's no progress yet. But this is now a convergent series. So if it's convergent, that means that it has some singularities somewhere in the complex plane. And they might not be on the real axis. They might be in the complex plane. And the idea is those singularities, imagine there's a pole here. That means that in evaluating this integral, you have to decide, of course, what to do with the contour. But you might get a contribution, which is e to the minus t at the pole divided by g. So suddenly you've developed an exponentially small non-perturbative contribution starting from a perturbative series. Okay? So that's what we call non-perturbative physics. So in other words, the Borel transform is actually extremely physical. It's now a function whose singularities are exactly the non-perturbative physics of our problem. Okay? So we're all very familiar in physics that Fourier transforms are extremely physical. We have a very deep understanding of what it means to go from time domain to the frequency domain or position domain to the momentum domain. It's like that here, but now with a Laplace transform. We can go between perturbative domain and non-perturbative domain using these Borel transforms. Okay, some examples. let's do quantum mechanics perturbation theory in the most familiar examples that we do when we're learning quantum mechanics. So the simplest example is the Zeeman effect. You take your hydrogen atom, put it in a constant magnetic field. Again, we all do first and second order calculations in our classes. If you look at high orders of this, you discover that the coefficients grow like 2n factorial and they alternate in sign. If they alternate in sign, it means that the singularities of the Borel transform, once you've removed this 2n factorial, are actually on the negative Borel axis. So they don't contribute directly to that integral. And so the physics of this is that when you apply a magnetic field, you indeed shift the energy levels, and these are the Zeeman, lead to the Zeeman splittings in atomic physics. But if you apply a Stark effect, remember what I said before about the Stark effect, the coefficients grow like 2n factorial, but they don't alternate in sign. And that has a consequence that the singularities of the Borel transform now are on the positive axis. So your integration contour went through those singularities. And so you produce an imaginary, because of the 2 pi I in Cauchy's formula, exponentially suppressed term, which must be there because it's the physics of ionization. In an electric field, you can ionize. In a magnetic field, you don't ionize. So there's a very simple physical interpretation. This is very much along the lines of Dyson's argument, that applying Dyson's argument to this problem, you would say, is the Stark effect perturbation theory divergent or convergent? Well, you would say it must be divergent, because if it was convergent, then you would never see ionization. End of story. Okay, so that's the essence of Dyson's argument. Now, if we apply this to instanton physics, because that's what most people think of when they first think about non-perturbative physics, here are the two famous problems when we teach about instantons. There's the double wall potential in quantum mechanics and the periodic potential. And because of tunneling between these neighboring wells, what would have been a single energy level in this well here is split by tunneling into two levels. And of course, because we can tunnel to infinitely many degenerate levels, it becomes a band in the periodic potential. And these exponentially small splittings due to tunneling have an overall amplitude which is exponentially small given by the action of this tunneling solution from one well to the next. So that's a summary of instanton physics. But in fact, if you try to do perturbation theory to high orders in one of these wells, you discover something interesting. First of all, it's divergent. Well, by this time, that shouldn't be surprising. But the rate of divergence is not in powers of the instanton action, it's in powers of twice the instanton action. Moreover, the perturbative expansion coefficients don't alternate in sign, they're non-alternating. But we decided on the previous slide that non-alternating was a sign of instability. But these problems aren't unstable. There's no metastable states here. So what's going on? Well, there's a very beautiful observation by Bogomolny and Zingerstan and Fateev and Brazan and people in the early 1980s, that actually what's going on here is that if you just do perturbation theory, you develop an imaginary exponentially small piece from Borel summation, but it's actually canceled exactly by something in the 2 instanton level from an instanton-anti-instanton interaction, which you can only have at the 2 instanton level, because instantons and anti-instantons attract one another, which destroys this instanton gas picture of the instanton calculation. And so the observation was that, in fact, these two things cancel one another. And this is the first view of the analytic continuation properties of a trans series. When you combine perturbation theory with the instanton gas picture, there's a problem, but it's actually canceled between a contribution from the perturbative sector and the non-perturbative sector. The only way that cancellation can happen is if the perturbative sector and the non-perturbative sector are related to one another. If they weren't related to one another, they couldn't possibly cancel against one another. So this is a very important, very beautiful observation. But it turns out it's even deeper than this. That if you look more closely at these levels, and not just focus on the ground state energy as those people had, note that in the semi-classical limit, this is a very high barrier where you're looking very deep down in the well. So tunneling is suppressed. These are exponentially small, these factors. Then actually we can consider not just one energy level, but there would be n harmonic energy levels in this harmonic well here or here. And each of them is affected by tunneling. So this is just the lowest band, but there's another band, another band, another band, another doublet, another doublet. And so the energy levels should be characterized not just by the coupling, which is telling you the height of the barrier, but also by the label of which perturbative energy level you're talking about. And so you get a series in H bar with coefficients that turn out to just be polynomials in this n. And then you get this exponential splitting. So plus and minus tells you the upper level, the lower level, or the top of the band and the bottom of the band. So this is the standard non-perturbative instanton correction. But now we learned that we can also study fluctuations around that. And then there's a 2 instanton, 3 instanton, 4 instanton, et cetera, which I can't fit on the slide. So that's what these dots are. An amazing, fairly recent result is that, in fact, this is an example of resurgence, because this fluctuation about the first instanton can be completely expressed in closed form in terms of this formal expansion. So this is a divergent series in H bar with coefficients that depend on n. This is a divergent series in H bar with coefficients that are functions of n, and they're not independent of one another. In fact, they're related in the sense that if you give me this, I can immediately write down this. And the expression looks a little bit complicated, but it has a natural structure that we now understand. And this is completely general. And it's much, much stronger than what I said before about large order growth related to low order terms. This is, if you give me 3 terms here, I can give you 3 terms here. If you give me 4 terms here, I can give you 4 terms here, etc. It's completely explicit expression relating these. And this is a very strong form of resurgence. And it's not just at the 1 instanton sector. It continues to all orders in this trans-series expansion. And the next order, there are logarithmic terms. And beyond, there are powers of logarithms. So this is established well for this instanton problem, this instanton problem. It actually generalizes to a whole class of problems. And here, since we're in Chennai, or I'm virtually there, I can't resist mentioning a connection to Ramanujan, is that he developed this generalized theory of elliptic functions. And in his notebooks, he lists these 3 examples of expansions of these modular exponential factors in series. And Bruce Berndt, who edited those notebooks, put this nice cryptic comment that he didn't know why Ramanujan was even thinking about these problems. And we now understand that this is actually a very important structure in supersymmetric quantum field theory and quantum mechanics, that actually this example corresponds to the periodic potential. This example corresponds to the double well. This is a triple well potential, and this is a cubic potential. And these are the simplest genus 1 quantum mechanical potentials, and they correspond to different numbers of fermions in 4-dimensional n equals 2 supersymmetric quantum field theory. And it's exactly the same structure. And it's really just another example of Ramanujan coming from a different universe, that he was doing something very fundamental that turned out to be extremely important, 100 years later, just out of the blue. So in terms of resurgence, this is really quite remarkable, because if we go back to this raindrop picture, what I'm now telling you is that we're now studying a problem where there's an infinite number of raindrops, because there's an infinite number of orders of this instanton expansion. And at each order of the instanton expansion, we can study the fluctuations, right? And now I'm telling you that if you know the fluctuations around the trivial saddle point, let's call it this point, I can just write down for you the fluctuations around any other saddle point at any order, even though there's an infinite number of saddle points. Okay, I mean, as I said, it's astonishing, but you can check it, and it's now well understood very well understood for a certain class of models. So this gives you a little bit of courage that maybe there is some truth and something behind this idea of resurgent, because it could easily have failed here, because we're now dealing with an infinite dimensional system. So let's think more boldly now. Let's think in terms of quantum field theory directly. could it be that it makes sense to think of this functional integral not as just a generator of perturbation theory and to try and rebuild perturbation theory back using Borel summation, but why not go directly to a sum over these saddle points, these thimbles? So what would happen if you could, there's a question mark here because this is a pseudo formula. This is what we would like to be true. If you could make sense of this deformation of contour in the infinite dimensional context, remember that a steepest descent contour is where the imaginary part of this is kept fixed. If the imaginary part of that is kept fixed, then doing this integral on that contour by Monte Carlo should be straightforward because it was the imaginary part that was causing the oscillations and ruining this probabilistic interpretation. So the imaginary part, the phase should come out of the integral for each thimble. So you're left with a completely well-defined Boltzmann weight type factor. There would be a complex Jacobian factor, but that's not the dominant contribution, so that's okay. You have to sum over all thimbles. This coefficient here is probably the most problematic term in this expression, because remember the Stokes phenomenon. The Stokes phenomenon said that inside this function here, there are other parameters, maybe a chemical potential, a temperature, an external magnetic field, an external electric field, an external gravitational field, whatever. As you vary those parameters, we could hit the Stokes phenomenon, that maybe suddenly some new non-perturbative effect appears or disappears. And that's manifest by this intersection number or coefficient for this thimble might suddenly go to 0. And so understanding that is one of the deepest questions here. That is being explored example by example at the moment in field theory. So remember, these Lefschetz thimbles are supposed to be these functional steepest descent contours. And in principle, on such a thimble, the path integral should be better defined and computable. How would you generate one? Well, one way to do it would be this complexified gradient flow. So you take your fields with their space-time coordinates x, you introduce a new parameter, sort of like a Langevin flow time, and you solve this nonlinear differential equation that the complex conjugate of the variation of the action, so this would be 0 at a saddle point by definition, but away from a saddle point, this is non-zero. But this flow equation will flow towards or away from a saddle point. And putting the complex conjugation here is what enables you to fix the imaginary part of the thing in the exponent. Now, lattice gauge theory people have well-developed techniques for gradient flow, not for complexified gradient flow, but for gradient flow. And so a certain set of people are working very hard on these gradient flow techniques in the complexified domain for applications in field theory. And there's been some recent progress in this direction. And I'm very hopeful that this may be one of the most practical applications of resurgence in field theory. So let me show you an example. Already 10 years ago, there's very beautiful papers by an Italian group and a Japanese group, more or less at the same time, studying the four-dimensional relativistic Bose gas. So that's a complex scalar field theory. It has a sign problem. It's a well-known sort of standard problem in this field. And they just took the simplest approach to look at the leading thimble and used Monte Carlo on the thimble and were able to obtain evidence for the phase transition. It's harder to see on this, but these are essentially identical plots, but the dots here are a little bit harder to see from the two groups. And the results were comparable to specialized algorithms that were developed specifically for this particular model. More recently, people have studied other quantum field theories, working their way up towards things like Yang-Mills and gauge theory. So here's an example of the 2D Turing model. So this is an interesting model that's asymptotically free. It has a sign problem at non-zero density, has some features of QCD-like theories, but of course in two-dimensional it's much more accessible. And these people, Alexander and Bazar et al., were able to use these thimble ideas to control both the silver blaze phenomenon of this transition at the chemical potential related to the baryon mass, and other features of this Turing model phase transition. And there's a very recent Reviews of Modern Physics summarizing some of this progress. And honestly, I think this is one of the most immediate regimes of quantum field theory where Resurgence might have some practical impact. But let me mention, in a real field theory, we're interested in a path integral that just doesn't have one coupling constant in it. It may have mass parameters, more than one coupling constant. We may have a chemical potential, a temperature. So now we're dealing with parameters, multi-parameter trend series. And this hasn't even been touched by mathematicians. I mean, even in the finite dimensional context, this question is completely open territory, terra incognita. But what can happen? We can think of this like a physicist. Imagine you introduce one more parameter. So there's a very familiar approach in quantum field theory for non-perturbative effects called large N. And from statistical physics, this would be seen as some sort of thermodynamic limit, that you won't see phase transitions in a finite system, but in a thermodynamic limit, the system can develop a phase transition. So we can actually ask this first simple question in this direction, which is, let's take a coupling constant and N. And let's think of taking some thermodynamic limit. But now we have two parameters, so you can think of different limits. You can take N fixed, and H bar small or large. You can take H bar fixed, N small or large. You can take them both in different directions. For example, this 't Hooft limit is very interesting, where you take H bar to 0, N to infinity, keep the product fixed, but the fixed could be big or small. And that's one way to interpret phase transitions. And these would be Stokes-like transitions. And what we expect would be that the trans series on one side of a transition should look completely different from the trans series on the other side of the transition, again, based on the analogy with the Airy function. So let me show you how this actually works in detail in this periodic potential problem, because this is very familiar. So here's just a quantum mechanics problem, cosine potential, energy, and H bar. So we can divide through by H bar squared. And so we can think of 1 over H bar squared as the height of the potential, if you like. So here's a picture of the energy levels as a function of H bar, and N labels which band we're talking about. So deep down in the well, so that here's the periodic potential, deep down in the well, the bands are exponentially narrow. So here's N equals 0, the 0th band, the first band, the next band, the next band. And it's basically a harmonic oscillator. So it's N plus a half times H bar. So it's half H bar, 3 halves H bar, 5 halves H bar, 7 halves H bar, okay? But as we increase the energy or increase H bar, the bands widen and widen and widen. And if you look way above the top of the barrier, now the potential is becoming irrelevant and the spectrum is basically continuous. And we have very narrow gaps. Okay. And now if you look near the top of the barrier, where this dotted line is, you might notice that the width of this band is now equal to the width of this gap. The width of this gap is equal to the width of this band, and so on. I don't know if you can see it by eye, but it's true. And what's happening here is that the one instanton approximation is very good here. As you increase H bar or increase N, you need to take into account all of these instanton effects tunneling between neighboring wells. But what happens up here? Up here, there are no turning points because the energy is above the potential. But in fact, there are turning points, but they're in the complex plane. E can be equal to cosine, even if E is bigger than 1, because cosine can be bigger than 1 in the complex Z plane, okay? And so in fact, if you look at those complex turning points, evaluate the action between them, lo and behold, the exponential of that gives you the width of these gaps. So what's going on here is that down here, the physics is governed by real instantons, the familiar ones we all learn about. Up here, the physics is dominated by complex instantons. And there's a phase transition here, and the phase transition happens when H bar times N is 8 over pi in this normalization. And there's an honest Stokes phase transition where the physics is governed by real instantons. And here, the physics switches to be governed by different saddle points, complex instantons. And now we have broad bands and narrow gaps. This is a very beautiful example. It contains all of the physics we understand and tells us something about what we might expect in field theories, but we can calculate everything here. And it's an honest phase transition. And this happens in the famous Gross-Witten-Wadir unitary matrix model. The physics here is essentially the same. So I'm coming to the end, so I think I'm going to have to conclude. Let me just give you one more example, if I can steal just a couple more minutes. There's this other very famous paper from Heisenberg and his student Euler back in the mid-1930s, before quantum field theory was even understood. They calculated non-perturbatively what we would now write as this infinite sum of one-loop diagrams, what we now call the one-loop effective action. They actually wrote down directly the Borel sum integral representation of this sum. And they noticed that there was an imaginary part to this effective action if the background field was electric, not magnetic. So this was like Dyson's argument and the Stark ionization. And so this perturbation theory had to be divergent in order to generate an imaginary part in the presence of an electric field. Now, what happens if you generalize this to have an extra parameter? So you take a monochromatic electric field. So now we have two parameters. And this problem was first studied in the context of ionization from shortly after the development of lasers by Keldysh. But then Brezin and Itziksen, and this was Edward Brezin's PhD thesis, in fact, was to apply that work of Keldysh to the QED problem. And they noticed that the pair production rate, the vacuum decay rate, took this famous Euler-Heisenberg-Schwinger form multiplied by some function of this combination of the frequency and the field strength. And when this parameter is small, it became the familiar one that we associate with tunneling. But when gamma becomes large, this function here developed logarithmic behavior, and the exponential of a logarithm undoes itself to become a power. So what you thought was non-perturbative is in fact perturbative. So this is the applied field raised to a power which is twice the binding energy. The binding energy in this system is 2mc squared divided by the photon energy. So this is multi-photon vacuum decay. And this is almost identical technically to the previous example of this periodic potential, because we have a periodic in time potential here. And you can really interpret this as the physics being governed here by a real saddle point and changing here to being governed by a complex saddle point. And this is the example I was working on many years ago when I first came across the ideas of resurgence, because I needed a formalism which was able to take care of these complex saddle points. And there are experimental proposals right now being developed at SLAC and at DAISY to combine the various high energy electron beams with very intense lasers to probe exactly this transition region. And these experiments should happen within the next 5 years. It's very exciting. There have been many other developments. I don't have time to talk about them. Many other examples in quantum mechanics, matrix models, quantum field theory. So far, Resurgence seems to be holding up in some aspects. You can compute more than you can in other contexts, but there's no sign of absolute failure yet where they easily could have been, because we're now dealing in this, we're working in this regime where there are essentially no mathematical results to guide us. It's really exploratory mathematical physics and theoretical physics. All right, let me jump to my conclusions. I'm sorry to go over by a few minutes. So what is resurgence? At one level, it's just a better form of doing asymptotics, a more powerful, stronger form richer form of asymptotics. From the physics point of view, it tells us that the relations between perturbative physics and non-perturbative physics are even deeper than we first thought. It's extremely well developed and understood in the context of differential equations and integral equations by the mathematicians. It's starting to be applied in many contexts in quantum mechanics and field theory, string theory. Personally, I'm quite excited about the applications to problems in lattice quantum field theory. More recently, I've been working with one of the mathematicians in this field, Ovidiu Costin, working on ways to improve extrapolations where we only have finite amount of information in perturbation theory to try and extrapolate that into the complex plane using ideas of resurgence. But the basic outlook that I hope that this will give us some new understanding and maybe some new computational access to some of these problems under extreme physical circumstances where we can't just use perturbation theory and where standard Monte Carlo techniques aren't currently working. So with that, let me conclude. And again, congratulations to the Institute on this celebration. Thank you.
Thanks, Gerald, for this very beautiful overview of the fascinating research that you have been doing for these years. And thanks for telling us about all of these. So now we are open to questions. Yeah.
Hi. At one point, you mentioned a paper by Konstevich in your initial slides. So, were you talking about the paper where he talks about complex metrics and how weak rotations, and we can use the notion of complex metrics, and how he applies those ideas to do calculations in curved spacetimes? Was that the paper you were referring to?
There's actually a series of works, and actually a lot of this is not yet written. But you can find recent talks by him, for example, from a meeting at IHES a few years ago, and you can find by Google. But also some works with Jan Soberman. Basically, the idea is that in finite dimensions, one way of understanding which saddles are related to other saddles and how they contribute to an exponential integral in multi-dimensions, but finite multi-dimensions, is to understand the intersection properties of these steepest descent contours. So it becomes a problem in homology theory. So one of the ideas there is to try and extend those techniques to infinite dimensions. And now, I basically told you what I know in detail, but that's one of the approaches that he and his collaborators have been developing. A lot of these things are not yet written. He's talked about it in talks, and he's given a very beautiful description of this Lefschetz thimble construction, even in finite dimensions, and its relation to Borel summation. And he's actively thinking about this and talking about it, and so that I'm talking not just about one particular paper, but there's a set of papers, and there are papers that are not even yet written.
So one more question. So when we apply the idea of the Euclidean path integrals, we can basically calculate the thermodynamic quantities like entropy and so on. So in the context of, let's say, gravity, it's not really giving us any microscopic picture, but it is giving us the right answers for the entropy. Does it do the same thing for QFT systems as well? Do we get some sort of a microscopic picture of the QFT systems or quantum systems when you use the Euclidean version of the path integrals?
Well, this is a very good question, and there's no generic answer that says yes for everything or no for everything. But some of the examples, for these Euler-Heisenberg type examples of applying what's known as the Schwinger effect, are analogous to some of these problems you're referring to in gravity. And there, yes, we understand that there are complex saddles that give the dominant contribution, but I stress that all of these calculations, even the ones you're mentioning, are really talking about the dominant contribution. And my claim is that this should be something more. If you look beyond just the dominant, say, other saddle, and even look at fluctuations around that dominant saddle, it should be able to tell you something about other saddles and even their fluctuations. And there should be this even richer structure which is underlying there, but it's beyond, I think at this point, it's beyond most people's computational access to study that in detail, except in idealized problems. And so there has been some progress in the context of these Schwinger effect type calculations. But in general, non-equilibrium systems, this is an active field of research and there's no definite answer. But if you believe that these path integrals are resurgent, then okay, it's there. The question is how to verify that or show that that's not true, and if it's not true, understand why it's not true. These are just current cutting-edge questions, and there's no answer that I know of.
So basically, like more than the computational side, like we don't know much about the physical aspects, like the actual microscopic degrees of freedom or as such from the path integrals.
But then the idea here is that if we can understand this type of approach, we might learn something about that. That's part of the goal here, right?
Yeah.
But given that there is no other approach that so far works, there's not much to compare with. And so, for example, I claim that these experiments that are going to be done at DAISY and SLAC will actually tell us something, because there have been absolutely no experimental precision experiments in this regime of quantum field theory. We understand QED, of course, very well for things like T-2, and we understand the standard model very well for thermodynamic properties like masses. But barring what we know about heavy ion collisions, there's essentially no experimental direct access to this extreme non-equilibrium regime of field theory. And these experiments will give us really precise information about that regime that contains some of the related questions that we have in these black hole gravity systems of back reaction, as you say, the microphysics of what's going on here. So these are important developments, I think.
Thank you very much.
Yeah, thanks for the question. Very good question. I'm sorry there's no precise answer.
Yeah. Further questions?
I have I'm not sure I've actually understood really this connection between the perturbative and non-perturbative physics. But you mentioned the saddle points repeatedly. So is it essential to have a saddle point? If you just have an absolute minimum, this technique doesn't work, or was it just an example?
So this comes back to the Stokes phenomenon. So a minimum could turn in, so first of all, a minimum is a special case of a saddle point, right? A minimum is a stationary point that just happens to have some property of the second derivative. If you have some parameter in your problem, as you vary that parameter, that minimum could turn into a saddle point, for example. And so what this statement is that we should generically study the saddle points, because if there is a saddle point, why does it or doesn't it contribute? So for example, here's a very specific problem. In Yang-Mills theory, right, Euclidean Yang-Mills theory, we understand very well the instantons. They're completely classified. These are the minima of the action, of the Euclidean action, right? However, it's also known, and this is a very deep result of Cliff Taubes and Karen Uhlenbach and Sidney, that the Yang-Mills action has saddle points. And it's completely regular, completely finite action. They're even real, but they're saddle points. Nobody knows what they mean. And yet, if you write down for me the functional integral of, say, just pure Yang-Mills theory, I can show you that there are real gauge field configurations that are saddle points. And now we should be able to say, what do they mean? They're saddle points. They should mean something. If they don't mean something, there must be a good reason why they don't contribute to things we want to calculate, like a mass gap or something like that. And this is a completely open question. I mean, it's now since the early 1980s that these solutions have been known to mathematicians. Physicists just don't know what they mean. And so I think that goes along the lines of your question. In general, if you have any integral that's the exponential of some function, and that function has critical points, those critical points are important. And Stokes tells us that we should be able, we need to understand all of the saddle points, not just the minimum. This is particularly important in the relation between Euclidean quantum field theory and Minkowski quantum field theory, because what is a minimum is a saddle point in general.
So I had a further question about that. So you mentioned that if you have the solution around one saddle point, you could actually predict those at the other saddle points. So was that related to?
That's the conjecture, yes.
Yeah, but is that coming from causality? I don't quite see the connection between, because they can be independent saddle points, right? So, or is it also coming from this connection between perturbative and non-perturbative physics? And my other question was, I didn't quite understand the Borel connection. Was it just the technical way of suppressing your large coefficients, or does that give you something beyond that?
Okay, so that's many questions. Let me start with Borel.
Sorry, I mean, you can choose.
That's fine. So Borel representation is one particular way of regularizing divergent series. It seems to be the most practical way in applications. And so it's just a way of regularizing. Think of it that way. It brings the problem into a form that you can control and now analytically continue. It's good from the physics point of view because it actually defines what you mean by non-perturbative physics. Non-perturbative physics equals singularities of the Borel transform. The reason being, if you have a Borel transform with a singularity, it's multiplied by an exponential factor because of the Laplace transform. Therefore, that singularity will contribute something like e to the minus the location of the singularity divided by the parameter, so non-perturbative. So if you like, it's a definition of what non-perturbative physics is. And so it's simply a fact that perturbation theory is generically divergent. You can have special integral models where things are tuned such that the divergence goes away, but these are set of measures 0 and they're very specialized. So if it's generically divergent, we need some way to control it. And so Borel summation is the way to control it. The Borel summation gives you the non-perturbative saddle points. And so in that, already at that level, they're coming from perturbation theory. So we already see that there's some relation between them. But the ideas of resurgence is that there are very precise connections between the different saddle points that come from deforming these contours. Now, again, in the Airy example, this Stokes example is very beautiful. It illustrates a lot of the ideas here. Remember that when that parameter x was positive, only one saddle point contributed, right? This is this very deep Stokes phenomenon, that as you vary parameters, you're sweeping your contours through the complex plane, and you could cross a new saddle point, and now you get a contribution from that saddle point. Or if you go the other direction, contribution from another saddle point might disappear. And so clearly that will generically happen. But when you're in multi-dimensions and even infinite dimensions, it's not clear that all of them will be related to all of them. And now it becomes problem specific. That generically they're all related, but I can actually, if I had more time and if I had a blackboard in front of me, I could show you some examples where some of these saddle points are actually disconnected from others. These tend to happen in some problems that have a certain sense of integrability in them. So when I say that they're necessarily all connected, that's the generic statement. And in the problems of differential equations and integral equations, it's very well understood how to tell which saddle points are connected to which other saddle points. But in quantum field theory, at this point, there's no general way to just look at a Lagrangian and say, yes, this is connected to this, and this is not connected to that. And the best example is Yang-Mills. There are saddle points, we have no idea what they mean. How are they related to instantaneous? We don't know.
Thank you.
Yeah.
Hi. So you have given an example about this Zeeman effect and the Stark effect. So for the Stark effect, you're saying it's a divergences, but also for the Zeeman, it's also divergent, but alternating. But then the non-perturbative effects are captured in that non-alternating series. Why is there no non-perturbative aspect in the alternating divergent series? Can you explain?
Yeah, it's because in the original integral representation, the integration was along the positive real Borel parameter axis, and the singularity due to the Zeeman effect, due to the magnetic field, is on the negative axis. So you simply don't go through that. So there's no contribution from that singularity to your integral, and your integral is giving you the energy. Whereas for the electric field, the singularities appear on the positive axis, so your Borel transform integral goes through that, and you get a contribution. So this is what I was saying just before. This is the Stokes phenomenon, that as you rotate the contour, you can pick up a contribution once the contour goes through one of these singularities. So it's the best way to think of it is in this Euler-Heisenberg example, where apply it to the Zeeman effect also. So you've got a constant electromagnetic field, right? So if you have either electric or magnetic field, the only Lorentz invariant is E squared minus B squared, right? Because E dot B is 0 if you only have one or the other. So your answer is a function of E squared minus B squared, right? Now, as you change, you can just call that F squared, right? And now the difference between a magnetic field and an electric field is changing F squared to minus F squared, right? Because you've either got E squared or you've got minus B squared, or vice versa. So that explains why in one case it's alternating, in the other case it's not alternating, right? So think of calculating in some constant electromagnetic field, doing perturbation theory. And now you have an integral with some Borel transform function, and this is exactly what Euler and Heisenberg did. And if that F squared is, I guess, negative, it's an alternating series, your integral doesn't go through that critical point. So there's no contribution from that. Right? You can find a steepest descent contour that doesn't go through that point. So even though it affects the integral, you get a different value from the integral due to the magnetic field. You don't get a non-perturbative term. Whereas when you rotated your F squared so that you're just an electric field squared, not minus a magnetic field squared, now your contour goes through those saddle points. In fact, there are an infinite number of them. And you get exponentially suppressed contributions from each of those that are imaginary. And so that's the picture. This is basically Dyson's argument that if the background field is electric, there's an instability due to an ionization. If the background field is magnetic, there is no ionization, so there is no instability. The electron stays in the atom, it just shifts its energy levels. Okay, so that's the physics picture. That makes sense?
Yeah, thanks. So I have another question. So you are talking about this complex instantons. Mm-hmm. So in case of Young Mills, it has a topological connection. So this complex instanton, does they have this topological connections?
It's not understood as far as I know. And in fact, the ones that I mentioned, these saddle points, they're actually real. I can write down for you an ansatz in SU3 for each field, such that it's a completely real field. It's a saddle point, and yet it's not an instanton. Actually, SU4 is even easier. Imagine a 4x4 matrix, right, for SU4. Take the upper right 2x2, just take the first 2x2 block on the diagonal and put an SU2 instanton in that block. And then take the lower right-hand corner 2x2 block and put an SU2 anti-instanton in that block. And 0 is on the off diagonal, right? Well, it clearly satisfies the Yang-Mills equations, right? It's completely real, completely regular, no singularities, zero action. Oh, sorry, not zero action. Twice the instanton action, but zero topological charge. But it's not self-dual, and it's not anti-self-dual. Okay.
Yeah.
So what does this mean? And there are more sophisticated ones when you go to SU2 or SU3, but it's clearly possible. And that's not even complexifying the fields. Right?
Okay. Yeah, thanks.
I want to ask a question in this connection with the instantons. They are all obtained from the ADHM construction. Okay? All the self-dwelling. One can get the instantons from the ADHM construction. Okay. Now, there is a norm transform or the norm Mukai transform from which you can deduce also the magnetic monopoles by a certain reduction, the time direction. Okay? So that's of much interest nowadays for people doing lattice calculations in the context of Calorons. So I want to ask whether this saddle points you're talking about, this results of, you mentioned some mathematicians' names, are they connected to magnetic monopoles?
Yes,
no?
in fact, that's a extremely good comment and question, because where this actually came from, Cliff Taubes, who's a mathematician at Harvard, first made this construction for monopoles and anti-monopoles using exactly what you just mentioned, using this relation between ADHM and NAM construction, but for monopoles. And he constructed solutions that were basically a monopole and an anti-monopole connected by some tube with a twist in it. And then Karen Uhlenbeck and used the connection between monopoles and instantons to sort of upgrade that construction in SU2 to construct a solution which was basically an instanton and an anti-instanton with a twist connecting them. And so, it's a perfect question. Yes, there is a relation. It's understood at that level mathematically, but my point really is not that. My point is we don't really understand physically what they mean.
That example is only applicable to SO4, the one you mentioned, because
no. Uhlenbeck applied it to SU2. So the example I gave was for 4x4 matrix, but it's even possible in SU2. But it's not so simple. It's not a matter of just putting an instanton and an anti-instanton. It's more complicated than that. But that's the result of Uhlenbeck and company, and it came from the work of Taubes about monopoles.
Okay. So are they related again to this Mukai transforms?
I don't know enough about that to be able to say. Sorry.
Are there any further questions? Audience from the Zoom, any questions? So I wanted to ask a very naive question. So when you want to extend this formalism to out of equilibrium physics, can you understand thermalization? Because then these are like fixed points in your theory. So this formalism, can it give an understanding of thermalization?
Yeah, so that's the hope. And I'm trying to think about that at the moment. So there have been some examples in what I would call baby examples, zero-dimensional or one-dimensional quantum mechanical examples of out of equilibrium. But to my knowledge, there hasn't been as much progress in the field theory context. And again, there's just too many open questions. This is a relatively new field, and people are developing different applications in different directions, and you're asking, this is one of the most important questions and one of the hardest questions, I think. So there's no answer yet. I think excellent problem for any of the students and people there to think about.
Thanks a lot for this motivation. So we already held you up for half an hour, but I think you enjoyed it and we enjoyed it a lot. I forgot to mention that you're an excellent mentor also. You had guided so many excellent PhD students and you've given such wonderful lectures across the world. So thanks for spending so much time and explaining so patiently all these beautiful concepts. And it has been a really privilege and honor for us that you kindly could give us some time to give this very nice colloquium as a part of our Institute's 60th year. And I hope to see you in person soon. Thank you very much.
Thank you, and thank you for the question.